Hello friends, welcome to this deep dive into Java 8 memory management. Today we will explore everything you need to know to effectively manage memory in Java applications, focusing on best practices, real world scenarios and optimizations for peak performance. Let's dive right in. Memory management in Java is crucial for both application performance and resource efficiency. Imagine a high traffic web application. Poor memory management here could lead to severe performance issues such as high latency or even application crashes due to inefficient garbage collection for memory leaks. By understanding Java's memory model, we can ensure applications run smoothly and efficiently. Today's session is designed for developers at all levels and will equip you with best practices and tools to optimize memory uses in your applications. Java's memory structure is divided into several key areas, each serving a specific purpose. We have the heap memory, which is where most of our objects are stored, and it's divided into the young generation and old generations. The stack memory is dedicated to method invocations and local variables, providing each thread with its own stack. Additionally, Java 8 introduced the Metaspace, replacing the old perm.gen space, which is where class metadata is stored. And finally, we have the code cache, where stores just in time compiled code to speed up method executions. Understanding how each part of this structure works allows us to manage memory efficiently and avoid common pitfalls. The heap is where most of the memory action takes place. It's divided into two main sections, the young generation and the old generation. The young generation in turn contains the hidden and survivor spaces, where new objects are allocated. The old generation is reserved for objects that have lived long enough in memory to survive multiple garbage collection cycles. For memory intensive applications like data processing or large scale analytics, understanding and tuning heap memory can significantly boost application performance. By ensuring that objects only live as long as necessary, we can optimize memory usage and reduce garbage collection overhead. Garbage collection or GC is essential to Java's automatic memory management. Java 8 offers multiple garbage collectors including serial, parallel, CMS and G1. The G1 garbage collectors, which is Java 8's default, offers the best balance for most applications, particularly large applications. By configuring G1 GC with option like plus uses G1 GC, we can minimize pause times and optimize performance. Later, we will explore practical examples for tuning GC settings to meet specific application needs. Let's focus on young generation GC, also called minor GC. This process is frequent but typically fast, collecting short-lived objects from the hidden space. If our application has many short-lived objects, we can optimize by configuring the size of the young generation to prevent frequent unnecessary garbage collections. By reducing the GC frequency, we keep our application running smoothly and avoid performance spikes caused by frequent memory reclamation. In contrast to minor GC, full GC affect the old generation and is more resource intensive. When objects accumulate in the old generation, we experience longer pause times, which can degrade application performance. The G1 collector provides configuration option like you can see it in the slide as code example. This setting is especially useful in applications where response time are critical, like e-commerce or financial applications. By carefully tuning these parameters, we can strike the right balance between memory uses and application responsiveness. Java 8 introduced the Metaspace, which stores class metadata. Unlike PermGen, the Metaspace can dynamically expand based on application needs, preventing the infamous out of memory error in PermGen. However, it is important to remember that excessive metaspace growth can still create memory pressure, as it competes with heap memory for resources. To prevent overuse, we can set an upper limit shown as in slide. By keeping the metaspace controlled, we avoid memory bloat, especially in applications that load many classes at runtime, such as plugin heavy systems or enterprise applications. Let's look at some best practices for efficient memory management in Java 8. First, we should minimize objects creation, especially in loops, to reduce garbage collection frequency. Instead of creating new objects each time, reuse objects where possible. Also, for string manipulations, it's best to use string buffer instead of concatenating strings, which is memory inefficient. Finally, avoid common memory leaks such as unclosed resources like sockets or static variable holding objects references. By following these practices, we can optimize memory uses and reduce the risk of memory leaks. Despite of best practices, some common pitfalls can lead to memory issues. Memory leaks are a prime example, often caused by unclosed resources or static variables holding unnecessary references. Over the time, this issue degrades application performance, causing sluggishness or crashes. For example, unclosed socket in a network application can quickly lead to memory exhaustion. To avoid these issues, always use try with resources for automatic resource cleanup and be cautious with static variables. By keeping our code clean and well managed, we prevent these pitfalls from causing long-term problems. Effectively, memory management is not complete without monitoring. Tools like JConsole and Visual VM allow us to monitor memory uses and GC activity in real time, giving us insight into how our application uses memory. Heap dump analysis, on the other hand, helps us identify memory leaks and inefficiencies. By regularly profiling applications, we can detect potential memory issues early and adjust accordingly, ensuring the application remains efficient over time. Now, let's see how memory management plays out in real world scenarios. In high traffic web application, for instance, optimized memory uses and minimal GC pause times are essential for handling large user loads without lag. Another example is financial trading platform, where even small GC delays can impact trade execution. In both cases, effective memory management practices help ensure smooth operations, faster response times, and better user experience. To wrap up, we have explored the key aspects of Java 8 memory management. We looked at the structure of memory, including the heap, stack, and metaspace, and discussed garbage collections and its impact on performance. By following best practices and avoiding common pitfalls, we can make our Java applications more effective and responsive. Regular monitoring and profiling further ensure that we stay ahead of potential memory issues, enabling us to build scalable, high performance applications.